Okay, so good morning, everyone.
Morning.
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 So we have already started chapter 12 last time. We discussed about the definition of solutions, some terms like saturated, supersaturated, unsaturated. We also discussed about the energetics of solution and how the nature of the substance affects solubility. Uh, Discussing about likes dissolves likes. We also discuss about the effect of temperature and pressure on solubility. Okay, we have a calculation on the so-called Henry's law, and if I'm not mistaken, we end up with a different expression of concentration units of solution, where we have molarity, mass percentage of solute, molality, and mole fraction. So you're going to have some sample calculation in the lecture slide recorded that will be posted in class by the end of the week. Okay, so we're going to continue with the next part of this what we call solution. So we're going to talk about colligative properties. Okay, so if we're going to look at the definition of the colligative properties, these are just properties, okay, that depend on the concentration of solute, molecules, or ions in solution, but not on the chemical identity of the solute. So what does it mean? These properties usually go up or down depending on the amount of the solute. So if you add the amount of the solute in solution, these properties can either go up or go down. And usually, if you're going to look at these colligative properties, they are just based on the physical properties that you know, and you just add some sort of a word to describe what happened, okay, to this property. So for instance, you have here vapor pressure lowering. So we have discussed vapor pressure in uh, chapter 11, okay? We also known what a boiling point and a freezing point means. So when we say boiling point elevation, okay, when we say freezing point lowering, in other books, the term that they use there is freezing point depression. So what does this tells us, at least these three colligative properties? So when there's a change in the amount of the solute, the vapor pressure usually lower for a given solvent, okay? If it's a boiling point elevation, okay, the boiling point, okay, usually is elevated, okay, due to the increase in the amount of your solute. And we have freezing point lowering. That means the freezing point lowers. So the only one that is odd here is osmotic pressure, but you could say that we can get that property from the pressure. So we're going to discuss each of them one by one today, okay, on how they affect or how the amount of solute dictates these so-called colligative properties. So the first thing that we're going to discuss is the vapor pressure, okay, the vapor pressure lowering. So we all know that if we're going to compare the vapor pressure of solution, it is usually less than the vapor pressure of the pure solvent. Why? What could be the main reason there? Why is the vapor pressure of solution less than the vapor pressure of pure solvent? So if you're going to look at the composition, if you say pure solvent, what does it mean? Anyone? When we say pure solvent, what is the percentage of solvent in pure solvent? Anyone? So if you have a pure solvent, it is 100% pure solvent. Okay? Now, what happened if you have a solution? Your composition in terms of pure solvent will now be less than what?
Less than 100.
It's going to be less than 100. And usually, the pressure depends on the amount of your solvent. So, the less the percentage of your solvent, usually the less is the vapor pressure of the solution. Because what happened there, the vapor pressure is usually coming from the contribution of your solvent. So if you're going to add the solute there, okay, the vapor pressure of your solvent decreases. Okay, so when the solute is non-volatile, the vapor pressure of a solution is the mole fraction of the solvent times the vapor pressure of pure solvent. So here we use the unit mole fraction. If you have a solvent, pure solvent, what is the mole fraction equal to? Anyone? What would be the mole fraction equal to if you have a 100% solvent only? Okay, your mole fraction would be equals to 1. So that means whatever, okay, the vapor pressure of the solvent, since it's only made up of solvents times 1, so that is equals to the pressure of your solution. So what happened to the mole fraction of your solvent as you add more solute? The mole fraction decreases. And if it decreases, it's going to lead to a decrease in the vapor pressure of the solution. Because if you're going to look from this calculation, everything comes from the vapor pressure of the solvent. So if the mole fraction decreases, how does the mole fraction decreases? Okay, how does the mole fraction decreases? Anyone?
By adding the solvent?
By adding the solvent? I don't think that's how it is. Because if you're adding a solvent, it's still solvent. So how does the mole fraction decreases? You add,
adding the solute, my bad.
Okay, you add more solute. So if you add more solute, the mole fraction of your solvent decreases. So if this goes down, this one is what we call constant. This will also go down. Okay. Now, if you're going to have two liquids in a closed container, and the condition of your liquid is such as this one, you have a higher concentration of B compared to A, as shown here by the darker shading, but the pressure of your A, the vapor pressure of your A is greater than the vapor pressure of your B. So after some time, okay, if you have this condition, a closed container, it will establish equilibrium. Okay, so what happened here? The gaseous solvent will condense in a more concentrated solution until the vapor pressure and concentrations are equal. So what happened here? If the vapor pressure of A is greater than B, so that means more of A will vaporize. Okay, so what happened to this vaporization? So after sometimes, the tendency for them is they go to the more concentrated solution. And they will only stop, okay, once they establish this, what we call equilibrium, you will see that the volume of the A here is less than compared to the one that's B. But when they establish already the equilibrium, the pressure will now be the same and the concentration will now be the same. Okay? Now, in what way we also look at this, what we call vapor pressure lowering. So for instance, you have, let's say, pure acetone here. And then compare it with acetone with water. So if you're going to what we call look at the differences of their volume after you leave it standing in an open environment for some time, which one will have the less volume?
Acetone.
Okay, so this one would have less volume. Okay, now which one will have a lower vapor pressure? A or B? If we're going to compare the vapor pressure, the pure solvent and the solution, which one has a lower vapor pressure? Is it A or B?
B.
Okay, it's B. Now the question is, what makes the vapor pressure lower? Compare it to what we call A. A is pure acetone. B is acetone with water. So what happened here for A? So you have an acetone, it's easier for it to
Vaporize.
vaporize, leave the liquid phase, go to the gas phase. But for the B, what happened? The presence of your solute there prevent some of the acetone to leave from the liquid phase to the gas phase. So in addition that there's also less of what we call acetone compared to the pure solvent, okay, there will be an interaction, okay, between the acetone and whatever solute that they have there. Okay, maybe another way to do it is if you, I don't know if this is applicable at this time, you are in the cinema, okay, so it's easier for you to leave the cinema if you're alone. But if you have a companion, it will take you a while to leave the cinema. So just think of it that if you're alone, you're just pure solvent. But if you have a companion, okay, you have a solute with you. So the effect of your solute there is, first, it makes the concentration or the mole fraction of your solute less. And then second, the interaction, okay, also leads to this vapor pressure lowering. So it's not easy for your liquid to already leave from the liquid phase to the gas phase, because the presence of another substance prevent you to do that. The interaction that you have, it would prevent you from doing that. Okay. Now, if you're going to look at this vapor pressure lowering, this is usually how you have it, and you call this Raoult's law. So Raoult's law is another, we could say, gas law that is usually used to describe an what we call ideal solution. Now, the question that you may ask yourself is, what is an ideal solution? You can go back to the definition of Raoult's law. An ideal solution is any solution that obeys the Raoult's law. So what does this mean? So it's just the same as what we call the Dalton's law of partial pressure. You still what we could recall the Dalton's law of partial pressure? The Dalton's law of partial pressure says that the total pressure is just equals to the sum of all individual pressure. Now, the Raoult's law, or what we call an ideal solution, okay, the vapor pressure of a solution is just equals to all the sum of the vapor pressure of the solute and the solvent. But unfortunately, most solution don't obey the Raoult's law. Okay, remember, what's the root word here that makes it unrealistic? The ideal solution, right? We always have this word ideal, ideal gas, okay? Ideal boyfriend, ideal girlfriend, okay? But sometimes we don't live in an ideal world, right? We live in a real world. So such thing as ideal are only what? Ideas. They exist in your imagination. So if we have this what we call Raoult's law, if you're going to look at here, so the vapor pressure lowering, which is denoted by the difference, okay, or the change here, delta P. So that is just equals to the vapor pressure of the pure solvent and solution. Okay. So what does it mean if you have what we call an ideal solution? That is just equals to the pressure of the solution and the pressure that was what we call results from the difference between the pressure of the pure solvent and the solution. So we know that the pressure of the solution is from the mole fraction times the pressure of the solvent. So if we're going to look at the delta P here, we can put it, denote it as that one. Okay? Because earlier, this is what we have. The P of solution is equals to the mole fraction of the solvent times the pressure of the pure solvent. But if we want to determine what's the vapor pressure lowering, so it's just equals to the mole fraction of the solute times the pressure of the solvent, the vapor pressure of what we call a solvent. So in question, you have to be very careful with the wording. You can ask the question, what is the vapor pressure of the solution? Or you can ask the wording, what is the vapor pressure lowering? So if it's vapor pressure, you're going to use this equation. If it's vapor pressure lowering, you're going to use this one. So that's the difference that you have there. Okay. And if you're going to look at here, the vapor pressure lowering is directly proportional to the solute concentration. So if the concentrations of solute goes up, what happened to the change in the delta P of the solvent? It also goes up. Or if we're going to look at the vapor pressure of the solution, it will what? Up, down. If you increase the mole fraction of the solute, what happened to the vapor pressure of the solution? It will what? Go up or go down? Anyone?
Will it increase?
Okay. So here, if this goes up, the vapor pressure lowering goes up. But what will happen to the vapor pressure of the solution? Will it go up or down? The vapor pressure will go down. Because as this goes up, this goes down. Okay? Because when you add this and you add that one, you have the vapor pressure of your solvent. Okay? So let's try to see here. Eugenol. So you are asked here, what is the vapor pressure lowering at 20 degrees Celsius of a solution containing 8.56 grams of eugenol in 50 grams of ethanol? And the vapor pressure of ethanol is 20 degrees Celsius. At 20 degrees Celsius is 44.6 millimeter mercury. So how are we going to look at it? Okay. So I just what we call have to take an important call. Okay, I'll resume in 2 minutes. Sorry for that. They just want to confirm that I have a negative result from my COVID testing. So let's try to look at the problem that we have here. So you're asked, what will happen? Okay, what will be the vapor pressure lowering at 20 degrees Celsius if you're going to add 8.56 grams of eugenol in 50 grams of ethanol? So the question is, what is being asked? Is it the delta P or the P? Anyone? What is being asked?
The delta P.
Okay, how about the others? What is being asked in the problem?
I also think it's delta P.
Okay, so since the word there is lowering, it is the delta P. But for your what we call understanding, we can also get that one. Okay, so how are we going to look at the thing here? So the first thing for you to do is, I'm going to put a whiteboard just in case. So you're going to get the molality or the moles, okay, of the material that you have there. So you have there 8.56 grams divided by the molar mass of eugenol, so 164.22 grams per mole. So we could say that's eugenol, and this is ethanol. Ethanol would be what? 50 grams divided by 46.08 grams per mole. So if it's not given, the formula will be the one that is given. So you're going to get the molar mass of that thing. So what do you get here in the eugenol? Anyone? 8.56 divided by 164.22.
0.0521.
0.052 to 1, right? And then the other one would be, so this is around 1 point something.
1.134.
1.08, 4 or 5. So we need an extra number here. So that's 1.085.
85.
Okay, so everyone will agree that this is the solvent, right? And this is your solute. Because you can do it at mole fraction A, or this one is mole fraction B. Okay? So the next thing that we're going to do is maybe we can get the mole fraction of the solute. So all we need is 0.0521 over 0.0521 plus 1.085. And that will give me how many fraction? What's the fraction for that? 0.0. 1.085. So that will give me around 0.045. I can put 0.04581 because this is not the final answer yet. Okay, we can add an additional digit. So what we're going to do now is we're going to get the delta P. And the delta P is just equals to X solute times P solvent. Right? So we're going to get the value 0.04581 times the P solvent that is equals to 44.6. So that would be equals to what?
2.04.
Huh?
2.04.
2.04 millimeter mercury. Analyze. Now, what if the one that is being asked, instead of vapor pressure lowering, what is the vapor pressure of a solution? So what you're going to do is, you're going to put this number instead here, and then you do the calculation. Okay? So in that case, what will be the number that you will get? So 1.085 divided by 1.085 plus 0.0521. I always get an error. Why? Is this what you get? 0.9542?
Yes.
And then you're going to multiply that with 44.6. So you will get around 42.56. Now we can also get it from here. If you're being asked what is the what is the vapor pressure lowering and what is the vapor pressure, all you need to do is what? 44.6 minus 2.04, because we have a relationship there. Delta P, or the vapor pressure lowering, is equals to the difference of the vapor pressure of the pure solvent minus the vapor pressure of your solution. So if you have that, you should also get the same value, like 42.56. Did you get that? Now, when we also describe this, what we call ideal solution, okay, another way of looking at this ideal solution is if, okay, your solute is non-volatile. When you have a solute that is volatile, you have what we call a non-ideal solution. So usually, if we're going to plot an ideal solution and non-ideal solution, so usually if you have it like this, so you have two components, okay? So like that one and that one. So this is A, this is B. Your ideal solution would have a plot like this one. So these are just, we could say, the total of the pressure that you have. But if you have a non-ideal solution, what happens? So this one would like this, and this one would have like this. So your total solution sometimes is greater than that predicted by the Raoult's law. When does it happen? Okay, when the force of your AB is much greater than, or we could say the force of AB is less than AA and AB. So usually that happens when you have a volatile solution. Now, in some instances, the total is much lower than the one predicted by the Raoult's law. So in that case, your A-B interaction, so when you say A-B interaction, how A and B interact with one another is greater than A and B. So what's the application of the vapor pressure? You're going to apply this in your next chem. Okay, you're going to apply it in your what we call organic chemistry. So the first thing that you have there is we could say one application of this vapor pressure is if you do steam fractional distillation. So what happens sometimes if you mix two liquid, the resulting boiling point is much lower, okay, compared to the boiling point of each of them. So it's much easier for them to collect at a much lower temperature. So that's the application of having this vapor pressure lowering. And if you're going to look also on this what we call vapor pressure, you can see that it's just dependent on the amount of the solute. The more solute, okay, the lower will become the vapor pressure of the resulting solution. So question on that before we go to the next colligative property. The next one that we have is, I think I showed here the thing. So when you're going to compare the vapor pressure of the pure solvent, usually this one, but okay, if you're going to look at the vapor pressure of the solution is much lower. And because of this, it results to the other two colligative properties. So as you could see here, so this is the freezing point of the pure solvent. So if you make that solvent into a solution, the freezing point becomes lower. Okay. And in terms of the boiling point, if you have the pure solvent, the boiling point of pure solvent is lower. If you make it into a solution, it will become higher. Okay. So what is the application of this thing? Maybe right now, this is really very common. What is the everyday application of this freezing point lowering at this time of the year? Anyone? Anyone wants to guess? So what do you usually put in the snow?
Salt.
Okay. You put some salt. Okay. So what happened? So when you put the salt, okay, the snow to remain in the solid form, okay, must achieve a lower temperature. So usually the more salt that you got, okay, the harder for the snow to remain in the solid form because its freezing point is much lower. So what you do, you're trying to make the freezing point lower, and in that case, the snow cannot achieve that, so it will become liquid. It will going to melt. So that's the application here. Okay, so the more solute that you have, the more salt that you have, the easier for the snow to melt, because for them to remain in the solid form, they have to achieve that lower temperature. So that's the science behind this what we call freezing point lowering. Another application here is, I don't know if you have an ice cream maker. So the homemade ice cream maker that I have is, they have a container here, and then you put the ice cream here, and then we put an ice, and then a layer of what we call salt, and then you put an ice, and then a layer of salt. So the idea there is you're keeping the temperature low, so the ice, or what we call the ice cream, remains in the solid form. Now for the boiling point here, elevation, I don't know if you know how to cook. So usually if you're what we call doing a stew or soup, when the water or the solution starts to boil and you add salt, what will happen? What will happen to your stew or soup when you add some salt?
It'll help it boil faster.
Okay, it will have boiled faster or will stop boiling. So those who know how to cook or have experienced this when they cook, okay? So usually when you add some what we call salt there, they will stop boiling. And then after some time, what? They will start to boil. Here's what happened. So you add some salt there. So that means the solution needs to achieve a much higher temperature for them to start to boil again. So the boiling point of them was elevated. And if you want to add more salt again, so what will happen? It starts to boil and then it's going to what we call achieve boiling at a higher temperature. No, I mean, when you add the salt, it stops it to boil. Okay? And the solution will only start to boil after it achieves the boiling point now, which is a little bit elevated of the solution. Try to what we call observe that thing. Okay? So those are just the applications of this freezing point lowering and boiling point elevation. So the way that you're going to do is, based on the wording, the freezing point of the solution will either, the boiling point will go up and the freezing point will go down if you have this what we call solution. And there is a corresponding unit or equation for that. So the boiling point of a solution is higher than the boiling point of the pure solvent. So you have here the boiling point elevation. So this delta TB, this is just what? Boiling point of solution minus boiling point of the solvent. And as you could see here, what do you think is the unit that we use here? Anyone? We're going to use the unit molality. So that's the reason why we have to include it as a concentration unit. Now Kb here, that's your boiling point constant. And it is given for a particular compound. Okay? Now for the freezing point, how are we going to describe delta Tf? Because this one is delta Tf and delta Tb. So this is just boiling point solution minus boiling point solvent. So if it's a delta Tf, it's just freezing point of what? Freezing point of solvent minus freezing point of the solution equals to KFM or MKF. And again, the freezing point constant here is usually given or known for a given substance. So let's try to solve problem in these two colligative properties. So we still have this what we call eugenol. But its case here, it says here, if the solution is 0.575 molal, what are the freezing point and the boiling point of the solution? So the freezing point and the boiling point of pure ether is negative 116.3 and 34.6 degrees Celsius respectively. The freezing point depression and boiling point elevation constants are 1.79 and 2.02 degrees Celsius per molal respectively. So how are we going to solve this thing? Okay, we're going to use the delta Tf equals to KFM and delta Tb equals to kbm. Okay? So what we're going to do, I'm going to put the whiteboard. And then we're going to solve the problem. So molality is given as 0.575 m. And then Kf is given as 1.79 degrees Celsius per molal. And you're given the freezing point of the solvent, which is equals to negative 116.3. And then we're also given the Kb, which is equals to 2.02 degrees Celsius per molar, and the boiling point of the solvent, which is equals to 34.6 degrees Celsius. So what's the one being asked? The FP solution and the boiling point of the solution. So we're going to solve it in terms of delta TF equals to KFM and delta TB equals to KBM. Now we need to break down what is delta TF. So it will be what? Freezing point of solvent minus and then we're going to put the values. Okay, so we know this as negative 116.3 degrees Celsius, but we don't know this one because that's the one that we're looking for. Kf is 1.79 degrees Celsius times molal, and molality is 0.575. So what do we do here? What is 1.79 times 0.75? 0.575. Anyone?
1.03.
1.03. So that means we're going to leave this on one side. Okay, so this will be a negative. So when you move it here, it will be what? Plus 116.3. So how do you remove the negative on this sign? You're going to make this into a negative sign. So you end up with 117.3. Did you get that?
Yes.
Yes.
Now, does this value make sense that this is lower than the freezing point of the pure solvent? Because the only way for you to know that you're correct is your freezing point of this of your solution should be lower than the freezing point of the pure solvent. So negative 117.3 is lower than negative 116.3. Now, boiling point, the same thing, but I'm going to put the number right away. So you don't know the boiling point of your solution, okay? And you know the one in the solvent is this one. And then you multiply it with 2.02 cm, okay, times 0.575 m. So what do you get there? 2.02 times 0.575. So that will be 1.16. Am I right? So what will happen? You can transpose this by adding both sides, the boiling point of the solution is equals to 1.16 plus 30.60. And if you get that, you will have 34.60 plus 1.16. So that is 35.8. Analyze. Before we go to the next one, a problem that is similar to your next experiment, experiment 14. Question? Now, as you can see, 35.8 is higher than 34.6. So the next thing that we have is this one. In a freezing point depression experiment, the molality of a solution of 58.1 milligram anethol in 5 gram benzene was determined to be 0.0784 molar. So what is the molar mass of anethol? Now, the freezing point depression is a very good technique to determine the molar mass of, let's say, an unknown. All you need to do is know the amount of your unknown, okay? And then know the amount of your solvent, and then look at the changes that it has, the corresponding changes that it has if you add your solute to it. So if you're going to look at this, what's the definition of our molality? Molality is mole solute over kilogram solvent. So what is given here? Because the one that's being asked here is the molar mass. So if I'm going to break down this equation that we have here, so you have molality equals to mole solute over kilogram solvent. So what I'm going to do, I'm going to combine molality times kilogram solvent. And on the other side, I'm going to break down moles as mass over molar mass. Does that make sense? Because the one we're looking for is here. So if we're going to break this down, just one straight equation, what will happen? I'm going to move molar mass on the other side, and then I'm going to put the mass here, and then I'm going to put the molality times kilogram solvent. So that's the one-shot way of solving this. But there's another way, the step-by-step way. So if you're going to look at the one-shot way of solving it, so we end up with what? 58.1 milligram, which we're going to convert to gram. And then divided by the molality that you have there, that's 0.0784 moles per kilogram. And then you have to convert 5 grams to, for every 1,000 grams, you have 1 kilogram. So that's the one-shot equation to solve this problem. So what do you get? Anyone? Okay, so you get 148. So that's grams per mole. If you're going to look the unit, milligram, milligram, gram, gram, kilogram, kilogram. Now, how do we do it the step-by-step way? So we can start with getting this, multiplying it with this one. Like if we start from here, we get the moles. So the moles is equals to molality times kilogram solvent. So if we do that, what's the value that we have? 5. Again, you divide it by 1,000 because you need to make it into a kilogram times 0.0784. So that will give you around 3.92 times 10 to the negative 4 moles. So now you have the moles. So moles, when you break it down, is equals to mass over the molar mass. You have the mass, you have the moles, so you leave the molar mass on one side. So you have mass here, you have moles here. So the mass is 58.1. And you're still going to convert it to gram. And then you divide it with the 3.92 times 10 to the negative 4 moles. So what did you get? Did you get 148? Anyone? What did you get in your calculation? No, it should still be 148. Everybody got that? The number there should still be 148. Did you get that? Are we done in this problem?
Yes.
Okay. So it's up to you what you're going to use. If you want to get the straight one like this one, but you have to be careful in the arrangement of the unit there. So the next thing that we have, it's still doing this molecular mass determination. That's the notion that you're going to have in your experiment 14. You're going to be given the unknown and you're going to determine based on the what we call computer plot, which is the what is the molar mass of the unknown. So here we have in our example an 11.2 grams of sample of sulfur was dissolved in 40 grams of carbon disulfide. So the boiling point elevation of carbon disulfide was found to be 2.63 degrees Celsius. So what is the molar mass of the sulfur in the solution? And in addition to that, we are asked what is the formula of the molecular sulfur? And the boiling point elevation constant there was given for carbon disulfide as 2.40. So if you're going to look at this, it's just delta TB No, that's not the KFM. My bad. Oh no, it's KB. So delta TB equals to KBM. So based on this, you don't know the molality, but you can get the molality based on the thing here. So if you want to get the molality is just equals to what? Delta TB over KB. So what is delta TB? So you have here the boiling point elevation of 2.63. So it's this one. That itself is your delta TB. And what is KB? It's given here as 2.40. So if you're going to look here, you're going to cancel the Celsius, you're going to have the molal, and that would be equals to what? Around 1 point something, 2.63 divided by 2.40. So that is 1.09 6. You follow? Now, the next thing that we're going to be asking here, so we have the molality now. So what we're going to do now, we know molality as moles, solute, kilogram solvent. So what else do we have here? We have this one. We have this one. We can break this down. So we have here the mass over molar mass. We also have the mass. So the way that we're going to do it, we rearrange this one. We have a molar mass equals to, how do we arrange that one? Mass over molality times kilogram solvent. And then we replace it with the given value 11.2, okay, the 1.090696, and then the 40 that you need to make into a kilogram. What do you get there? Anyone? What did you get? Any number from these operations? I put this one in the middle. So that would be around 255.5. Now, we have only answered the question, what is the molar mass? Now, the next question that we have is, what is the molecular formula of the sulfur? So the next thing that we're going to do, this is the molecular or molar mass. So the next thing that we're going to do is we're going to divide it with the molar mass or the atomic mass of your sulfur, which, if I'm not mistaken, is around 32.065. And what do you get from that? If you round it up, it would be around
8.
So that means your sulfur will be an S8. So that's the main use of your freezing point depression or boiling point elevation. They can also use to determine the molar mass of the unknown. So questions so far before we go to the last colligative property. Question? Pregunta?
Are you gonna open?
Testing. Okay, question?
Yes, sorry. Are you gonna open up assignment 2 that has problems like this?
No, because the other section is asking me to do something that is combined with them. I'm going to talk about that later. So the next and the last part of our colligative properties has something to do with osmosis. So if we're going to look at this osmosis, okay, it's just a phenomena that is common in many biological and chemical processes. So osmosis is just the phenomenon of solvent flow through a semi-permeable membrane to equalize the solute concentration on both sides of the membrane. So when we're talking about osmosis, we could say this is just the selective passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated one. So there should be a semi-permeable membrane. So the semi-permeable membrane would allow the passage of the solvent molecules, but blocks the passage of the solute molecules. So this is how the semi-permeable membrane looks like. So it will only allow to pass you the solvent, but not the solute. And usually it is going to be a movement from what? A dilute solution going to a concentrated one. So the water here is the solvent. And if we're going to look at it, the water will flow from left to right. So what happened here? This will become more dilute. So this is concentrated. This is at least diluted. Now, when we're talking about osmotic pressure, that's the pressure that you apply to stop osmosis from taking place. Okay, so we could say the pressure that you have here, that's really unusual compared to the other definition of the colligative properties. So if ever you have it here, so the water is the solvent, it flows from the beaker into the T-cell tube. So looking at this one, so the membrane that you have here is around here. So this is the water and this is the glucose concentrate, glucose solution. So the corresponding pressure that you have there to stop the osmosis from taking place, that's your osmotic pressure. So osmotic pressure is just equal to the pressure that when applied just stops osmosis. And osmotic pressure is a colligative property of the solution. So it's just this one. So what can you say about this equation? This equation is just a derivative of what? It's just a derivative of PB and RT. Because if you're going to look at this, wait, how does it happen? You put the B here. So the N over B is just your what? MRT. So the P that you have here is just the pi, that's just the pressure. But it's only applicable in the process of osmosis. So if in the vapor pressure lowering, you have mole fraction. In the freezing point depression and boiling point elevation, you have molality. In osmosis, you have molarity. And as you could see here, as the molarity increases, your osmotic pressure also increases. So there is a direct relationship between the amount of the solute with the colligative property of osmosis. Okay? So how are we going to apply this one? So usually you apply this in big molecules like this one. Dextran, they're used as what we call blood plasma substitute. So at 21 degrees Celsius, what is the osmotic pressure in millimeter mercury of a solution containing 1.5 grams of dextran dissolved in 100 ml of aqueous solution if the average molecular mass of dextran is 4.0 times 10 to the 8 AMU. So if you're going to solve this problem, it's just what? Pretty straightforward. Pi equals to MRT. So all you need to do is solve for this one. And the other materials or the other values are given there, although it's not directly, especially for the what we call molarity. So if we're going to look at the molarity that we have there, that's mole solute over the given volume. So you have there the given volume as what? 100 ml. And then the solute would be, if we're going to look at it, 1 gram divided by this one. So you have 1.5 gram over 4.0 times 10 to the 8 AMU. So if you're going to look at this AMU, that's just a gram per mole. And then you divide all of it with 100 ml, but you have to convert that to liter. And once you have that, you already have your MRT, so your M. So you can just multiply it with the corresponding R. So what's the R that we're going to use here? Anyone? What's the R that we're going to use here?
8.314.
Is it the 8.314 or 0.0821?
0.0821.
Okay. So this is not an energy problem. So you're going to use the 0.0821. And then you're going to multiply it with the given temperature, which is equals to what? 21 degrees Celsius plus 273 Kelvin. And the answer that you have there is still in what unit? What unit do you have there? Atmosphere. And the one that is being asked is osmotic pressure in millimeter mercury. So whatever you get there in the number, you just multiply it with 760 millimeter mercury times 1 atmosphere. And what do you get? So what is the one in atmosphere? What's the value that you get in atmosphere before we go with So 1.50 divided by 4 exponent 8 divided by 100 divided by 1,000. So I get around 3.75 there times 0.0821 times 294. So I get around 9.05 times 10 to the negative 7. Atmosphere. And if I multiply it with 760, I get around 6.87 or 6.9 times 10 to the negative 4 millimeter mercury. So that's the answer that you have to that question. 6.9 times 10 to the negative 4 millimeter mercury. So check. Now we can look at this, what we call osmosis. If we look at our cell, so there's a cell that is what we call isotonic. So the two solutions, they have equal concentration. Now cells sometimes are what? Hyper or hypo. So if it's hyper, you have more of the plasma. You have less water. So the water flows out of the system, and then this would what? Results to the collapse of your cell, or the so-called clination. And if you have a hypotonic solution, there's too much water in your cell, or you have the so-called hemolysis. Another thing that we can look at this thing, what we call osmosis, is in your cornea. So usually you look at the concentration of your body fluid in cornea and the aqueous humor. Now, so far in the colligative properties that we have discussed, we assume that there's no correction factor. So what does it mean? Whatever the value that we get, okay, that is the amount of our colligative property. But in reality, you have to take into consideration the nature of your solute, especially one that are what we call ionic compounds. What's the problem with the ionic compounds? They would form more than one particle per unit. So if that is the case, what happens is you have to multiply by a certain factor the colligative property that you have. So if you're going to look at this, this is what? Vapor pressure lowering. This is boiling point elevation, freezing point depression, and osmotic pressure. So in each of them, we added the so-called I. So I is the so-called correction factor. So what would be the value of your I? Well, it depends on how many ions do you have per unit. So if you only have a molecules, what could be the value of I? It's just equals to 1. But if you have ionic compounds like NaCl, which will dissociate to give you what? Na plus and Cl minus, your I value will be equals to 2. So you have to multiply everything by 2. Because you have 2 units that you have there in your solution of your solute. If you have, let's say, magnesium chloride, what is the value of your I? Anyone? So this will dissociate to give you what? Magnesium 2 plus and 2 chloride. So that would be, I would be equals to 3. And if you have aluminum chloride, So you will have Al3 plus 3Cl minus. So your I is equals to 4. So if you are asked question, which of the following has the lowest boiling point, assuming same molality, and your choices are NaCl, magnesium chloride. I put A, B, C here. AlCl3, and this one is sugar. So what will be your answer? What will be your answer? A, B, C, or D? If you have a question like that. Which of the following solution has the lowest boiling point, assuming they have the same molality? Anyone? Any takers? What's the answer there? So if you have a questions like this, the answer would be the D. Why? Because you have the lowest boiling point elevation here. But if the question here is highest, what is the answer? Anyone? Hello? Are you still there? Anyone? Okay. So if the question is now, which of the following has the highest boiling point, assuming same molality, the answer now will be C. Why? This one will give you 2 units. This one will give you 3 units. This one will give you 4 units. Where does those units come from? The ion compounds that you have.
What is the I for sugar?
1, because it's a molecule.
Oh, okay.
So those are the things that you have. This is applicable if you have the ionic compounds. You have to do what we call the I that we have there. So whatever calculations that you did, if the one that is given, let's say, is an ionic compound, then you have to multiply it by whatever ions or number of ions it releases. It's just like if you have 1 mole of NaCl, it will release what? 1 mole of Na plus and 1 mole of Cl minus. So in reality, you release 2 moles of materials from a starting material that is just 1 mole. Do you get that?
Yes.
This is where our chapter ends. So there will be additional recorded slide that will be posted in classes by the end of the week. Like this one, I'm going to answer that thing there. Okay. Now the last part that we have there is a colloid. This is not usually part of the exam, but it's a what we call a very good material. Okay. So how is it different from your what we call solution? Colloid is a little bit dispersed. And one way to what we call differentiate a solution from the colloid is the colloid exhibit this Tyndall effect. So what is this Tyndall effect? The scattering of light. So if you have a solution, you don't see it. But if you have a colloid, you're going to see it like this one. Now, the one that why I included this is because there's a lot of colloid around us. Okay. And the most example, the best example of the colloid that we have here is your soap. Okay. How do soap clean? So usually in the soap, you have the hydrophobic end and the hydrophilic end. Have you imagined? What do you think is the soap? Is it polar or non-polar?
Non-polar.
Okay. How about our body? Are we polar or non-polar? Have you imagined that? Is our body made up of polar or non-polar? Are we polar or non-polar?
Both.
Huh?
Both.
We can say both. Are we polar or non-polar? Anyone? What are we made up of? At least with respect to the soap. So imagine if we are polar. When we take a bath, you will see our ears or our face dissolving in water. So that means we are made up of non-polar molecules. That makes sense? Because if you say we're polar, then we're going to dissolve while we're taking a bath. We're going to dissolve in water. So we are made up of non-polar material. We are made up of fats. But inside it, you have the polar material. We are made up of the so-called bilipid layer. Okay? And the way that we do the cleaning here in the soap is usually they have a polar and non-polar component. So the one that do the cleaning one is the non-polar. Okay? So what happened there? You have the polar and the non-polar, and you also have a positive and a negative end there. But if you're going to look at the way that they clean, it is the non-polar sections that are usually being used. Okay, so the dirt with the soap, we have the so-called micelle to do it. And if we're going to look at an example of this emulsion, I have a thing here, but I need to end the recording, or else I have going to have a hard time in uploading them. Okay.